This video is going to contain various examples of experiments that can be done with waves, both springs and sound waves. First example is a Hooke's law apparatus. We attach a spring to a mass, and the mass is going to stretch the spring. So downwards we have a force of gravity. Upwards we have the force of spring. And that's going to be in equilibrium, so those two will equal each other. And force spring this time will be positive. So force of the spring is going to equal kx. That's Hooke's law. So the force of the spring is equal to the spring constant multiplied by the distance that the spring is stretched. So we have an equation that is y equal mx. So if we graph the force of the spring on the y, and that would be in newtons, versus the x, which is our x displacement, and that of course be in meters, we would get a straight line graph like this. Okay, and how do we get the force of the spring? Well, you guys know that the force of the spring will also equal mass times gravity. So it's a nice straight line graph, and the slope of this graph will equal k. Our next example, we have a tuning fork above a graduated cylinder that'll produce standing waves in this pattern here. We would have an antinode at the opening and then a node where the water barrier is. And our length L is going to be the height of the air that's above the water, and it'll be to the opening of it. So that's length L. Now, node antinode is 1/4 of a wave. Okay, so inside the tube here, there's a 1/4 of a wave. So L is equal to 1/4 lambda. And therefore, lambda is equal to 4 times L. So the equation here, frequency equals n times the velocity of sound divided by 4L is what we derive for the harmonic pattern. And then n is equal to 1, 3, and 5, etc. Okay, now where does that come from? Well, we know that the speed of a wave does equal the frequency times wavelength. Well, then I have the speed is equal to the frequency times 4L. And dividing 4L to the other side, we get this pattern. Now the n comes from the harmonic number. We have 1, 3, 5. We do not get even number harmonics inside of a graduated cylinder because we're only starting with 1/4 of a wave. So the next harmonic would be an antinode, node, antinode, node, which is 3/4 of a wave, and so on. So if we look at our equation here, I'll write that over here again. We have frequency. Let's choose the fundamental frequency, which is n equal 1. So if n equals 1, then the frequency is related to the speed of sound divided by 4L. So if we vary the frequency of our tuning fork and change the length of this, we could make a graph to get the speed of sound, which is what this variable here is. Okay, so I'm going to graph then accordingly the frequency versus 1 over the length. And that's the length of the column here. So we have a graph of y right here equals mx, but y is frequency. Okay, and that'll equal hertz. And then x is going to equal 1 over L, which will be meters to the minus 1. So let's do meters to the minus 1 here for the units. And this will be hertz, which is really reciprocal seconds, so I better do that. Reciprocal seconds like this. Okay, and we will get a straight line graph. Okay, so what's the slope equal to? The slope is going to be this right here. I'll just put dashed lines around it. So the slope of this line is going to equal the speed of sound divided by 4. And that's how you use a graduated cylinder to get the speed of sound.